The statistical control chart is an important tool that is most used in the quality engineering sector as a way to improve process efficiency and increase overall product quality. A control chart is comprised of several data points, as seen in the table presented here, that are organized in a sample number to resulting value relationship. The resulting graph should look rather jagged, which means that each point on the graph is independent of one another and no pattern among them should be noticed. It is crucial that each test is independent of one another because of relationships among the tests could skew the data by not showing as many outliers or showing more outliers than there truly are. This would defeat the whole purpose of the control chart because its goal is to display whether or not a process is in control and if changes need to be made. In a statistical control chart, there should be an upper control limit, UCL, and a lower control limit, LCL, and a central line. The first two lines are calculated values for y on the XY control chart that mark the boundaries as to whether or not a specific test point is in control. The central line represents the perfect center of the UCL and LCL, and it also represents a population mean that is calculated to be the value that is desired, whatever that may be. In this slide, we can see a control chart in action in the electrical engineering sector. In the experiment used to create this project, thermograms combined with control charts were able to detect how many times certain low voltage power distribution components were too hot or too cold to be functional. This experiment was able to show how many defects there were in the sample that was tested to determine if something is wrong with how they are being produced and if the defects were severe enough to require a redesign. Here we have a control chart derived from data produced in the studied research project. Notice that there are three lines that represent the UCL, mean value, and LCL. It can be observed that there is an outlier above the UCL which represents a sample component that operated at a temperature that was too hot to function properly. The components whose temperatures are calculated to be above the UCL are investigated, and it is usually found that the components had loose connections, poor installation, either they short-circuited or they contained load imbalances. The use of the control charts when analyzing thermograms help better identify if there are problems that tend to happen quite frequently that can be corrected by changes in the production or installation process. Not addressing these issues in the components could result in damaging entire machines and increases the risk of fire since we are dealing with electrical currents after all. Something to keep in mind when using control charts in the engineering field is that they are not capable of identifying what the exact problem with every single component might be. Since the chart is simply measuring the temperature of each component, we cannot tell what is causing the temperatures to reach alarming levels. It could be because of improper installation of the module, or it could be because of a short circuit in the component. We really don't know. More investigation would have to be done on each faulty component to determine the cause, and only after investigating the faulty units could we as engineers determine if there is a problem that needs to be addressed.